Welcome back to SEMIKRON's Power Channel. My name is James Wilford. Well, it was an exciting day at the Messe yesterday. Lots of questions, lots of buzz on the booth. As always, silicon carbide is on the agenda. Fortunately, last week I met with Stefan Hauser, our product manager responsible for silicon carbide. Let's hear what he had to say. Good morning. Welcome back to SEMIKRON's Power Lounge. Right now, I've got Stefan Hauser with me. We're here to talk about silicon carbide. Good morning, Stefan. How are you doing?
Good morning, James. Very fine, thank you.
Good. Stefan, it seems to me like people have been talking about silicon carbide forever, but it sounds like real products are starting to emerge. Where do we stand today with silicon carbide?
From my point of view, silicon carbide is probably the most exciting technology since the introduction of the silicon IGBT in the 1980s. It reduces your power losses. It can switch very fast, which means you can increase the switching frequency quite drastically, and the power density of silicon carbide components is huge.
Okay. So how, obviously there are TO220 packages around the silicon carbide, but how is silicon carbide implemented in power modules today?
Well, we have basically two different ways. One is a hybrid silicon carbide module, which means you keep your standard silicon IGBT and you combine it with a silicon carbide freewheeling diode. This already brings down your switching losses, the turn-on losses of the IGBT to something like 30–40%.
Okay.
The silicon carbide freewheeling diode basically has no switching losses. So this means at carrier frequencies of 30–40 kilohertz, you can really bring down your power losses, which means an increase of your efficiency. The second is a full silicon carbide module, which means also the standard silicon IGBT is replaced by a silicon carbide MOSFET. This can be combined either with a silicon carbide freewheeling diode or just the MOSFET on its own. This will even more reduce your losses, of course, and it will really triple your power density at carrier frequencies of 30–40 kilohertz.
Okay, and do we have people using them today at carrier frequencies of 30–40 kilohertz? So far I've heard of people going to 20 kilohertz, but not higher.
Well, it is a problem that in the past or now with the standard IGBT technology it might not be possible, but in fact there are applications where it makes a lot of sense to increase your carrier frequency. For example, if you think about power supplies for induction heating, for example, or medical power supplies for MRIs, they need high output frequencies and therefore also high carrier frequencies just by nature.
Okay.
Also there are applications like, for example, UPSs, solar inverters or auxiliary power supplies for trains, for example. There you have filtering on the output side, and just by increasing the carrier frequency you can reduce cost and space required for these filters.
I see, so no longer the IGBT is not dominating the bill of materials in terms of cost. That there are other things now that around what silicon carbide allows you to reduce the size of and therefore the cost of.
Of course, there's still a little drawback, which is the price for the silicon carbide module. I have to admit that.
Well, that's what I was going to say. There's certainly well, from what I've seen, it still seems like 3 or 4 times more expensive than standard silicon. So, where do we stay with that?
Yeah, to be fair, this is true. It is more expensive than a silicon module, but usually you have a benefit from this. So you compensate the higher cost for the module either by performance win in the application or simply by saving money on the filtering cost and space. So you can compensate that actually. And which is very important, you cannot just compare a standard silicon module by current with the silicon carbide module. So it is important to have an application knowledge and to have a close look on the application, have proper calculations done to really know which silicon carbide module is the right one for my application.
Okay, so do we have actual products released today, and if so, what's the range of those products?
Well, we can sample silicon carbide products quite easily. We have different baseplate-free modules, for example, the semi-top, which is available in press fit pins and also with solder pins. We have a mini-skip with a well-known spring technology, and we have a complete solder-free module, which is the SKIM 6393. So huge range of currents beginning at 10 amps, going up to 300 amps. Beside that, also baseplate module, we have the SEMIKRON 3, which is a 62 millimeter module, a standard module, and we can sample that easily.
Okay, brilliant. Stefan, thanks for taking the time to come in to see us today.
You're welcome. Thank you very much.
Thank you. And now back to the studio. Thank you, Stefan. Just after meeting with Stefan, I bumped into Thomas Hurtgen. Thomas Hurtgen is the product manager responsible for Miniskip. Thomas had mentioned to me it's now possible to go up to 90 kilowatts with a Miniskip for inverter applications. On the strength of this news, I asked him too to join us in the studio to give us a bit more detail. Welcome back to the SEMIKRON Lounge. I'm joined by Thomas Hurtgen. Hi Thomas, how's it going?
Everything okay, thank you, James.
Good, good. Thomas, before we move on to talking about the Miniskip Dual, I read last week that there are 24 million Miniskips in the marketplace. Where are they all?
25 million Miniskips in the field is really a success story of SEMIKRON. We have at least 16 years of experience with Miniskip. And Miniskip is used in a lot of applications like standard industrial drives, UPS and solar. And a lot of the top players, especially in the standard industrial drives area, are using Miniskips up to a power range of 40 kilowatt.
Okay, cool. So anyway, back to what you're here to talk to us about today. SEMIKRON is releasing the Miniskip Dual at PCIM. What's the Miniskip Dual going to do for our customers, Thomas?
Yeah, the basic idea of Miniskip Dual is to extend the Miniskip product portfolio up to a nominal chip current rating of 300 amps. So our customers are now able to use Miniskip up to 90 kilowatt, which provides really the customer a benefit, so in scalability of their drives, and eliminates the need of paralleling Miniskips to have a higher output power.
I see. I see. So where does Miniskip Dual fit in the overall picture of Miniskip?
So Miniskip Dual is the new member of the Miniskip family. So Miniskip Dual is a baseplate-less module with spring power terminals and provides actually all Miniskip advantages like solderless assembly, one or two screw mounting, and a PCB connection for the signal and for the power terminals.
Okay. Okay. So it sounds to me then like basically what we're saying is technology that was employed below 40 kilowatts is now possible to employ right up to 90 kilowatts.
Exactly.
Okay. So why would our customers want to do that?
So Miniskip is now available from 4 amp to 300 amp. Miniskip Dual is available in 650 amp, 650 volt, 1200 volt and 1700 volt. And yeah, so the Miniskip Dual power range is currently dominated by baseplate modules with screwed bus bars. And if you now replace the baseplate modules with Miniskip Dual, the customer is able to reduce the total inverter system cost.
So how does that work?
Yeah, the big advantage is, or the first advantage is that you really get rid of the bus bars by using standard PCB technology for connecting the signal and the power terminals. The one or two screw mounting of the Miniskip Dual enables really a faster assembly in the production line. So the assembly is much quicker with Miniskip Dual, and also the material usage in terms of screws which are needed for really connecting the PCB, the power module, and the heatsink is reduced.
Okay, brilliant. So it sounds like that's a real advantage for our drives customers to be able to use the Miniskip Dual.
Yes,
okay.
It's a big advantage.
Brilliant. Thomas, thanks for taking the time to come and see us.
Yeah, thank you very much.
We'll look forward to seeing you at PCIM.
Thank you.
And now back to the studio. Thank you, Thomas. Well, I better get things wrapped up here and get to the show. Another interesting day is in front of me today here in Nuremberg. Anyway, thank you for joining us. I hope to see you at the show, but if not, I look forward to seeing you tomorrow. For now, it's goodbye from Nuremberg.